Now, so for type 0 system, there exists a finite kp value, a finite error constant, that is your ks. What is the corresponding error? The corresponding error formula ESS is R by 1 plus kp. Kp is kv, ks. So if you substitute ks here, steady state error is R by 1 plus ks. R is the step magnitude. So unit step R is equal to 1. The step magnitude can be anything. You can simply substitute and you can get the steady state error. Similarly, we can take type 2 system. So type 1 system, type 0 system is completed, type 1 system. In type 1 system, P is equal to 1. So we can rewrite the gh of s function. Again, gh of s is equal to, numerator is as it is, ks into 1 plus s into tz1 into 1 plus s into tz2 and so on, dot dot dot. So in denominator we have s, 1s means it is type 1 system. S into 1 plus s tp1, 1 plus s tp2 dot dot dot. So this is the open loop transfer function, velocity error constant. So we know already type 0 system. For type 0 system, gh of expression is available to you. Now kv equation is limit s tends to 0, s into gh of s. So in gh of s we have ks into all 0 terms divided by all pole terms. But when you substitute in this equation, so s exists here, s into gh of s. So since you have s, when you substitute s tends to 0, that kv value is going to be 0. Therefore, whenever you apply ramp input to type 0 system, the corresponding error coefficient or error constant kv is going to be 0. What is the corresponding error? The corresponding error ESS is equal to R by kv, that is going to be infinity. Similarly, the third is acceleration constant, Ka is equal to limit s tends to 0, s square gh of s. Again, if you take type 0 system, if you substitute here, your Ka is going to be 0 and corresponding error is infinity. Next, type 1 system. In type 1 system, in the denominator gh of s function, s power p, the p value is 1. Then what will be the resultant gh of s? So gh of s numerator is as it is, ks into 1 plus s into tz1, 1 plus s into tz2 divided by s into 1 plus s into tp1, 1 plus s into tp2 and so on. So this is the open loop transfer function, and if you have formulas available, we will substitute it. The first one is kp. When you take kp is equal to limit s tends to 0 gh of s. But when you take the gh of s here, you will get all the terms 0, but denominator we have another extra s term, which results that kp is equal to infinity. When kp is infinity, corresponding error is r divided by 1 plus kp, that results in 0. Therefore, whenever you apply step input to type 1 system, then constant is infinity and its steady state error is 0. The second is velocity error constant, kv is equal to limit s tends to 0, s into gh of s. So you take gh of s type 1 system, you can cancel ss term, it results ks. Therefore, kv is equal to ks, s is a DC gain. And what is the corresponding steady state error? ESS is equal to R by kv, therefore R by ks. So R by ks is the steady state error for ramp when you apply the ramp input to a type 1 system. Similarly, acceleration constant Ka is limit s tends to 0, s square gh of s. When you take type 1 system here, so the value will be 0, Ka is 0, corresponding error is infinity. Now similarly, we can take type 2 system. In type 2 system, gh of s is equal to numerator is same, ks into 1 plus s tz1, tz2 and so on, and denominator we have to take s square because the p is equal to 2 in type 2 system. So 1 plus s into tp1, 1 plus s into tp2 and so on. So gh of s function is every time it is same only. So in type 0 system we have s power 0, therefore that is 1. In type 1 system s power 1, therefore you will get s in the denominator. Type 2 system we have s square. Now so Kp, what is Kp now? Limit s tends to 0, gh of s. In gh of s, denominator s square term we have. Therefore, Kp is going to be infinity and corresponding error r by 1 plus Kp is 0. And Kv, limit s tends to 0, s into gh of s. Again, if you take type 2 system here, one more 0 is coming, one more s is coming in the numerator. So that results in 0. So one more denominator is coming, that results in infinity. Then your steady state error is r by Kv, that is going to be 0. And acceleration error constant Ka, limit s tends to 0, s square gh of s. Now in this case you can cancel s square. Therefore you will get it as only Ks. So Ka is equal to Ks for acceleration constant. Now, so what is the corresponding error? So ESS is equal to R by Ka, therefore R by Ks. So we have a type 0, type 1 and type 2 systems. We have already seen all Kp, Kv, Ka values for all three systems. Now we can conclude that all Kp, Kv, Ka values depends on the DC gain of the system. DC gain is also called static gain or static sensitivity. Now, I want to prepare a table which consists of input and type of gh of s. So, let us take in this table, we have all types here, type 0, type 1, type 2. Similarly, you take step input, ramp input and parabolic input. And we try to fill this table, which is very important most of the times. By looking at this table, we can find out what is the error constant and also what is the corresponding steady state error. Now, type 0 system, step input. The results we already seen, right? So, we want to place the result here. We know that whenever you apply step input to type 0 system, there exists a constant Kp. Kp is equal to Ks and corresponding error is Es is equal to R by 1 plus Ks. Then what will be for same step input is applied to type 1 system, your Kp is equal to infinity, steady state error is 0. And for type 2 system, again same thing, your Kp is going to be infinity and your steady state error is 0. So I am applying step input. Whenever you apply the step input, we have to calculate only Kp values. Kp values or Kp is positional error constant for only step input. So that is why I said step input is also called a positional input. Now coming to the second column, I have ramp input. So ramp input is applied to type 0 system. We already seen that Kv is going to be 0 and corresponding error is infinity. But when you apply ramp input to type 1 system, yes, there exists a finite constant error constant Kv. Kv is equal to Ks and its corresponding error is Es is equal to R by Ks. Now coming to the same ramp input I am applying to the type 2 system. When you apply type 2 system, Kv is infinity and error is 0. So in this column I am taking only one error constant, that is Kv, because we are applying ramp input. Similarly, we can fill the last column, parabolic input. When you apply the parabolic input to type 0 system, your Ka is 0 and error is infinity. Similarly, for type 1 system, again Ka is 0, error is infinity, but you will get Ka is Ks for type 2 system and corresponding error is R by Ks. Now, if you closely observe with this, all the elements in this matrix form or table form, all the diagonal elements will have finite error constant and finite errors, and those error constants are only Ks. Ks is the system static sensitivity or static gain. So that system is your open loop transfer function, gh of a static gain. Now, so when you look at the lower diagonal elements, so lower diagonal elements, your error constants are infinities, whereas corresponding errors are zeros. Similarly, if you look at the upper diagonal elements, your error constants are zeros, whereas corresponding errors are infinity. So this table is very useful to understand the error constant concept and as well as its corresponding steady state error concept.